It's Monday, March 2nd, 2026. Chemists at King's College London have isolated an unusual aluminum compound that could help reduce industry's reliance on scarce metals. The work appears in Nature Communications, published January 30th, 2026. The key result is something called a cyclotrialumane, 3 aluminum atoms bonded together in a strained triangular ring. That structure is the novelty. Previous aluminum chemistry had monomers, dimers, and tetramers, but this trimeric form had never been made in neutral form before. 2 examples were synthesized, and both hold their triangular structure intact in solution rather than falling apart. This is molecular chemistry, not a new alloy or manufacturing technique. The aluminum here sits in an uncommon oxidation state, aluminum-1, where it can act as a reactive 2-electron donor. The team made it by reducing aluminum diiodide precursors with potassium and hexane at room temperature. One version came out at 82% yield, which is notably high for this field. What can it do? The cyclotrialumanes activate hydrogen gas, alkynes, and benzene. Methyl iodide and hydrogen react quickly at room temperature. The standout reaction is with ethylene, a key industrial building block. At room temperature and about 1 atmosphere of ethylene pressure, the trimer is completely consumed and a new insertion product forms at over 98% yield by NMR. With excess ethylene, the chemistry continues into 5 and 7-membered aluminum carbon ring systems that the authors describe as unprecedented in both transition metal and main group chemistry. Computational modeling supports the speed-energy barriers for the initial ethylene steps are just a few kilocalories per mole, consistent with the observed room temperature reactivity. The paper frames this inside a long-running push to get main group elements like aluminum to behave the way platinum group metals do in synthesis and catalysis. Lead author Claire Bakewell notes that aluminum is roughly 20,000 times cheaper than platinum or palladium, though she acknowledges that aluminum extraction is itself energy-intensive. One quick clarification on media coverage: some headlines say this work could replace rare earth metals. Rare earths are a specific group of 17 elements, including scandium, yttrium, and the lanthanides, best known for use in magnets and electronics. What this paper actually targets is a different supply chain problem: dependence on platinum group metals for chemical catalysis. Those are not the same category. The honest summary is this: a new, unusually stable and reactive aluminum platform that can activate small molecules and form ring products no one has made before, and which could, over time, point toward alternatives to precious metal catalysts in certain reactions. Real-world replacement would still require embedding this chemistry into scalable processes that work under industrial conditions. That work hasn't been done yet. But as a structural and mechanistic first, the result is genuinely significant.